The numerical technique we will use to solve the governing equations of fluid flow is the finite volume method. ANSYS Fluent uses this method, as do many other commercial CFD codes. And the basic idea of the finite volume method is to take your flow domain and divide it into little chunks or control volumes and apply conservation to each little chunk. And you do this using the integral form of the governing equations. The net result is that you get a set of algebraic equations, and we will see this in more detail later. At this point, you might be wondering, in the structural mechanics examples, we use the finite element method to convert the governing equations to a set of algebraic equations, and why not do that here? In fact, there are codes, CFD codes, that use the finite element method. It turns out that the finite volume method is perhaps preferred over the finite element method in CFD applications. That might be because it offers one big advantage, is in that it applies conservation directly rather than indirectly. So for each little chunk, it's applying conservation, and it conserves quantities in a discrete sense, and we will unpack this idea in more detail later. This in contrast to the finite element method, which does not necessarily conserve quantities for each little chunk or finite element. And we saw this in the case of conduction, where heat was not conserved for each little element. In our CFD case studies, we will use the finite volume method via ANSYS Fluent. We'll discuss the big ideas in the finite volume method by considering a simple example. I'll lay out what that example is in a minute. And by going to a simple problem, we can focus on the core fundamentals. More complex examples are based on these big ideas, and we'll keep coming back to these ideas as we solve problems in ANSYS Fluent. They form the building blocks of CFD and of the finite volume method. So it's important that you understand these big ideas well.